Atoms are the tiny building blocks for all materials, and how atoms are arranged affects their physical properties, which is crucial to materials engineering. To give you an idea of just how tiny atoms are, about 5 million hydrogen atoms could fit into a pinhead. In the basement of MIT Nano, there is a specialized microscope able to image materials at the atomic level. This microscope is the Thermo Fisher Themis Z Scanning Transmission Electron Microscope. Here's how it works. In order to achieve an atomic resolution, the sample used must be extremely thin, 1/1,000,000th of a millimeter, or 1/100,000th of a strand of hair. The sample must be this thin so that electrons can travel through and interact with the material. Once the sample is placed into the holder, it must be inspected to make sure the sample is loaded securely and there is no contamination that could degrade the microscope vacuum. At the top of the microscope column is the electron source, where the beam of electrons emits from. The electrons shoot out of the emitter and are accelerated to 70% of the speed of light, then focused into a small point by a series of electromagnetic lenses. As the focused beam scans over the sample, electrons travel through it and are displaced by atoms and scatter. The scattered electrons are collected by the electron detector, which then assigns a grayscale value to form the image. In the control room, you can zoom and focus on particular parts of the sample to identify atom activity and collect data. The more electrons that are collected, the brighter the image. Where there are no electrons, the image is dark. This is a video of material from a magnesium-ion battery. All of the light spots we see are atoms in their predicted positions. They appear to be stationary. However, when electrons from the beam collide with certain atoms, in this case metal atoms, they provide enough energy to move the atoms through the structure. Here it is dark, then a light spot appears, and that light spot is the metal atom, jumping in and out of its position. Being able to see this sort of phenomenon can tell you information crucial to materials engineering, from the building material for bridges and airplanes to electronics and biomedical devices.